Hi, welcome to this module. In this module what we will learn how to design and build a signal conditioning circuit for thermocouple to compensate for temperature correction. Now, thermocouple is a temperature sensor or it is used to measure the temperature. Same thing, there are RTDs, there are temperature sensors which are also used, but thermocouple is most widely used because of its ease of operation. It is low cost, it can be used from minus 200 degree centigrade to 2000 degree centigrade. It is exclusively used in automobiles and home applications. So, let us see how we can do the temperature correction or how we can design a signal conditioning circuit that can be used for compensating the temperature correction in case of thermocouple. So, if you see the slide, like I said, a thermocouple is a sensor for measuring the temperature. It consists of two dissimilar metals joined together at one end, which produces a small unique voltage at a given temperature. So, you can see here, which is junction J1, right, and you can see there is two different metal, right, iron and constantan. So, they are joined together, fused together to form a bead, and this bead is the measuring hot junction. This is where it measures the heat, okay, and there is a cold reference junction which is right over here, and then there is a voltage difference. So, it creates a difference in voltage, we will see that. Now, so it consists of two dissimilar metals joined together at one end, which produces a small unique voltage at a given temperature. This voltage is measured and interpreted by instrumentation. So, here the voltage is generated at this particular end and it is further connected to the instrumentation amplifier, mainly used for measuring high temperature of exhaust gas. It may also made from variety of different materials, enabling extreme temperatures, like I said, from minus 200 to 2000 degree centigrade. The four most common type of thermocouple alloys are: first is type J, which is iron constantan, which is exclusively used. Then we can also use chromal alumyl, which is type K. There is another called copper constantan, which is type T, and we have chromal and constantan, which is type E. So, four basic type of common type thermocouple alloys are shown here, right, and based on what kind of alloy you are using, you can name the thermocouple with J, with the alphabet J, T, K, E. Okay. So, you need to remember this. Now, to measure the output voltage V out, this is the difference between measuring hot junction, right, hot junction, which is right over here, cold junction right over here. So, I can measure V out, which is difference between hot junction and cold junction. Now, VH and VC are generated. VH, which is voltage here, VC, which is voltage here, right, are generated by temperature difference between two junctions. Therefore, V out is a function of temperature difference, which is V out equals to VH minus VC or alpha times TH minus TC, right. The temperature at the hot junction minus temperature at the cool junction. So, where alpha relates the voltage difference to the temperature difference. Now, this is what is called, is also called Seebeck effect, right. We have studied earlier in physics what is Seebeck effect, right. So, Seebeck effect, the most common configuration is shown in the figure 2, which is right over here, right, and the third metal, that is copper, is connected, introduces two additional junction to the system. You can see here we are adding a copper here, adding a copper here, right. So, there are two more junctions which are created right over here, but this junction will not have any effect on the output voltage, since two junctions are same type and are at the same temperature, right. So, adding two junctions with the help of copper wire will not really change the output voltage. Next is, since the thermocouple measures the temperature differentiality, the cold junction temperature must be known in order to determine the actual temperature measured at the hot junction. Now, if we want to understand what is the temperature differentiality of the thermocouple, or actually the thermocouple measures the temperature differentiality. So, the cold junction temperature must be known in order to actually measure the hot temperature, that is very important. So, if you see the slide, what we are talking about is that the cold junction temperature must be known in order to determine the actual temperature measured at hot junction. So, if you do not know the cold junction temperature, it is very difficult to measure the hot junction temperature. Now, the easiest way to measure the temperature of the hot junction is by maintaining the temperature of the cold junction at 0 degree centigrade, and is also called ice bath, and temperature is 0 degree centigrade. So, the easiest way to make the cold junction or measure the temperature of cold junction is you just put this cold junction in an ice bath. Now, we know the temperature of ice is nothing but 0 degree centigrade. So, this is the easiest way to measure the hot junction temperature is by maintaining the cold junction temperature at 0 degree. In general, the ice bath refers is served as a standard in thermocouple application, but maintaining ice bath temperature to 0 degree is impractical in most situations, and therefore, when the cold junction is not at 0 degree, the temperature of this junction must be known in order to determine the actual hot junction. If you do not know this one, if you cannot maintain at 0 degree, then what is the temperature of the cold junction, it is very important to know. So, thus the output voltage of thermocouple must be compensated to account for the voltage created by non-zero cold junction temperatures, right, and this is known as cold junction compensation. That is what we are looking at, the how to do a cold junction compensation. Okay. So, the idea here is if you do not have a ice bath and you cannot maintain the temperature of the cold junction at 0 degree centigrade, but if you do not know the cold junction temperature, then you cannot measure hot junction temperature. So, you should know the cold junction temperature. For understanding cold junction temperature, you have to use ice bath, but if you do not have ice bath, then it is impractical to keep it at 0 degree centigrade. Then what is the voltage created because of the non-zero junction temperature in the cold junction, we need to know, and to compensate that non-zero value, we have to do a cold junction compensation. So, in general, to implement cold junction compensation, the temperature of cold junction is measured by using other temperature sensors such as RTDs, thermistors or silicon ICs. In summary, cold junction temperature measurement device must be selected to match the requirements of the system, right. So, what are the requirements of the system? That it should be accurate, it should have temperature range, it should be less costly, and linearity, which are the significant consideration in selection process. It should be linearly changing with respect to temperature. So, these are some of the important parameters when we select a temperature measurement device for cold junction. So, now if for a given problem, how we can solve this? Let us see. So, for a K type thermocouple is to be used in a measurement system to obtain an output of 2 volts at 200 degree centigrade. Okay, this is a question. Design a signal conditioning circuit for thermocouples such that to compensate for temperature variations at cold junctions or reference junction using a solid state temperature as the reference for temperature correction. Now, what is that? Please note, the sensor has 3 terminal supply voltage Vs, output voltage Vb, and third terminal is grounded. The output voltage varies at 10 millivolt per degree centigrade. A K type thermocouple with reference 0 degree centigrade will be given as output given output of 8.2 milliwatt at 200 degree centigrade. Sensitivity is 41 microvolt per degree centigrade. These are the things given to us. Now, let us see how we can design a signal conditioning circuit for thermocouple such as to compensate temperature variation at the cold junction. Okay. So, given that the cold junction compensation for K type thermocouple is 41 microvolts per degree centigrade, which is already given, right, and gives an output voltage of 8.2 millivolts at 200 degree centigrade, also given, and the second sensor, which is solid state temperature sensor, which is a 10 millivolt per degree centigrade, which is also given, right, is used to compensate for cold junction temperature change. So, gain of the first differential amplifier is chosen in such a way that response of 2 sensors are made equal, and so mathematically if you want to make equal, then gain is nothing but sensitivity of second sensor divided by sensitivity of the first sensor. What is sensitivity of second sensor? Sensitivity of second sensor is 10 millivolt per degree centigrade. So, 10 into 10 raised to minus 3 divided by what is the sensitivity of first sensor? Sensitivity of the first sensor is 41 microvolt into per degree centigrade. So, we can write down 41 into 10 raised to minus 6. So, when you divide this, when you solve this, you have a equation value of 243.9 or approximately 244. Hence, the output of thermocouple is amplified with the calculated gain using non-inverting amplifier, right, as shown in the circuit. Thus, both sensor will follow the same sensitivity. This is the circuit, right, where the output of the thermocouple is amplified so that both sensors follows the same sensitivity, right. This is one. Now, to compensate temperature variation at the cold junction, the final output should be added with the voltage corresponding to the temperature, right. So, the final output should be added to the voltage corresponding to the temperature. So, this output voltage, both should be added to the circuit, as the second sensor has the sensitivity of 10 millivolt per degree centigrade. Any change due to temperature variation must be added to the equation. Thus, the output of first op amp and output of the second sensor is given to a summing amplifier as shown in figure. We can see very clearly, right, output of the first amplifier and the output of the second amplifier, output of first op amp 1 and output of op amp 2 is given to a summing amplifier, which is right over here, right. And to maintain 2 volts output, the gain of second op amp is chosen to be required output by input of the input voltage to the op amp. So, 2 by 2, which is equal to 1, right. So, here our gain will be nothing but 2 by 2 equals to 1. So, now in our experimental class we will see how we can use this whole circuit to compensate the temperature correction in case of when the cold junction is not at 0 degree centigrade. Okay. So, again if we quickly repeat it, what we have seen is how we can design a signal conditioning circuit for thermocouple to compensate for temperature corrections. Like I said, we first started with understanding what is a thermocouple, what kind of alloys are used for thermocouple, what is a hot junction, what is a cold junction where the output voltage is generated. Now, what is the problem? The problem is that the cold junction should be at 0 degree centigrade. Now, before that we have studied that the output voltage is nothing but Vh minus Vc equals to alpha times Th minus Tc, and alpha is nothing but the voltage difference due to the temperature difference. We have also seen that if you add the copper line to the metal A, metal B, what will happen? There is no different, it will not affect because both are at same temperature and both are of same type. So, the copper wire adding to the thermocouple is not going to affect our system. Then we have also seen that we have to keep the cold junction at 0 degree centigrade, which can be done by using ice bath, but it is very difficult to keep ice bath at 0 degree centigrade, kind of impractical in actual situation or most of the situations. So, we have to use another sensor to measure the cold junction temperature, so that finally we can measure the hot junction temperature, correct. And the sensor that we can select should have a better accuracy, better temperature range, it should be less costly and it should be linear. Then we have seen that if you want to design a signal conditioning circuit for a given problem statement, then how can we design such a circuit, and when you solve this you can have a circuit which is right shown here. And we will do this kind of experiments to an extent using a simulator rather than showing you actually, because we need to otherwise get the ice bath. So, it is kind of difficult, but anyway. So, this will be the end of this particular module, and in the next module we will see some of the applications, actually applications of op amp you can say, or we can say that how the analog to digital control systems, or how to analog to digital converter and digital to analog converter will work. Alright. So, for this particular module, this is the last slide. And please learn about this whole module, understand what are the stages to design such a signal conditioning circuit, and if you have any questions, feel free to ask me through the forum, and I will try to answer your questions. Like I said, this is just an example just to help you out how can you use the operational amplifier in favor to design your signal conditioning circuits. You can take many more examples and try to implement such circuits. Alright. Now, my TA discuss about the circuit design and perform a simulation. Then they will discuss about how the circuit operates. We have seen in theory in detail, but we just need to have a quick recall of how circuit operates. So, they will show you about that circuit operation and compare it with the simulation. To design the circuit using multi-sim, again we will ask our friend Sitaram.
So, now we will see the experiment on to design and build in signal conditioning circuit for thermocouple to compensate for temperature correction. So, that means we have to develop a signal conditioning circuit for a thermocouple. So, why do we require this signal conditioning circuit? To compensate for temperature correction. So, that means we should understand how exactly thermocouple works. Now, what will be the problem associated with the thermocouple? Then after that we have to think about how to correct that particular we have to introduce a correction factor in order to compensate for that temperature. So, that means if you recall what professor has already discussed about thermocouple, a thermocouple is a temperature sensor which can use to measure temperature. Of course, there are other different temperature sensors which we have also seen in this module. One is LM35, which is also a temperature sensor. Other temperature sensors like thermistors, RTDs are also available. But why a thermocouple is important? Because it can measure up to more than 1000 degrees centigrade. It depends upon what type of thermocouple combination that you use, what type of alloys that you use, like iron constantum or copper constantum. The range, the temperature measuring range will be entirely depends upon what type of alloy that you use, and the temperature ranges will be even higher. You can measure up to 1500 degrees, 2000 degrees centigrade temperatures too, which cannot be possible with other temperature sensors. But if it is a case, if we understand how the thermocouple works, it is easy for us to develop a signal conditioning circuit. So, to make you understand about how a thermocouple works, if you consider this is one, so if you consider this is one material, this is another metal. If you combined at two different junctions, so let us take the green is one particular material, other one blue is another material. If I create one node here and another node here, so that means I am joining these two thermocouples, two different metals. So, this forms one junction, this forms another junction, right. This is one junction, this is another junction. So, when we place this particular junction in one particular temperature and this junction in another particular temperature, depends upon the difference between these two junctions, the temperature difference between these two junctions generates an EMF in your wire, in this metal, right. So, that is what your Seebeck effect do. So, thermocouple generally uses a Seebeck effect. So, if you see the slide, if you look into the slide, so one particular combination, one particular junction kept at heat. So, another junction, if it is placing another reference temperature or a known temperature, it generates an EMF voltage. That EMF voltage entirely depends upon the difference between this junction temperature and this junction temperature, right. So, but what if your reference temperature is not at the known temperature? So, when you understand, in order to measure the temperature, one way is by looking into the output voltage of a sensor, right. So, for example, like say if the sensitivity of this particular thermocouple, K type thermocouple is 41 microvolt per degree centigrade, that means if I look into the output voltage of 41 microvolt, I can understand that the temperature is at, the difference in the temperature is 1 degree centigrade. Now, if I say the cold junction temperature is at 0 degree, which is known to me, right, and so that means the other junction temperature will be always at 1 degree centigrade. What if your cold junction temperature is not at 0 degree? Because it is very hard to always maintain the temperature, right, cold junction temperature at 0 degree, that is one thing. Or you can also keep it as a reference temperature or room temperature as a reference temperature, but even if you observe, the room temperature will always vary, depends upon the climatic conditions. It cannot be always at a constant at 27 degrees or neither at 25 degrees, it will always vary. So, that means that when you see the output voltage of a thermocouple, it is completely relative, it is not a absolute, it is a relative, it entirely depends upon your cold junction temperature. What if your cold junction temperature changes? Obviously, your output voltage will also changes. As a result, it is very hard to understand whether the change in the output voltage is either due to the change in your plant or due to the change in the cold junction. So, because of that reason, generally they use another temperature sensor, right, such as an RTDs or thermistors or other silicon type of ICs in the cold junction. So, by using those particular sensors, we will generate an output voltage, and that output voltage is corresponding to the change in the temperature in this cold junction. As a result, whenever there is a change in the cold junction, this particular output voltage from the temperature sensor, if you use as an input to added to the output voltage of thermocouple, we can compensate for the temperature variation in the cold junction. So, but what happens that the temperature sensor which is placed in the cold junction, the sensitivity of that temperature sensor may not be always same as the sensitivity of your thermocouple, right. For example, like say, for example, I will take, so consider this is my thermocouple, this is unknown temperature which we need to find, right. These two forms another junction, this two I am placing it on room temperature, right. One junction is at unknown temperature, one is at room temperature. So, if I measure the output voltage, this output voltage will always be proportional to difference between unknown temperature and room temperature. Now, if I know the room temperature value, I can obviously understand the output voltage. So, that means output voltage only now it only depends upon unknown temperature, because I know the room temperature, right. But if I consider the room temperature as 25 degrees centigrade, depends upon the climatic condition, the room temperature will always fluctuate from 25 to 30 degrees, or in other countries it may also go from 0 degrees to it will always vary from 20 to somewhere around 40 degrees centigrade too, right. As a result, it is very hard to understand the room temperature until unless you have another temperature sensor. So generally what they do is that they will place one more temperature sensor at the cold at the reference temperature, or near the at this particular junction, reference temperature junction. So, by measuring the output voltage from this temperature sensor, right, we can incorporate that particular temperature value at this point. So, as a result, we can easily find out output voltage. Otherwise, it is very hard to understand. By simply observing the output voltage, we cannot understand whether the change is due to the unknown temperature or because of the change in the room temperature, right. But what happens, whatever the temperature sensor that we use, the sensitivity factor may not be the same as a sensitivity factor. In this case, for example, like say if I take LM35 as a temperature sensor, the LM35 temperature sensor sensitivity is 10 millivolt per, sensitivity of LM35 is 10 millivolt per degree centigrade, whereas thermocouple sensitivity is 41, K type thermocouple 41 microvolt per degree centigrade. For example, like say if this is at 100 degree centigrade, if this is at 0 degree centigrade, right, if it is at 0 degree centigrade, so I should get an output voltage as 41 micro into 100 degree, right. So, this is 4.1 millivolt, but this one should give it as 0. For example, if it is at 10 degree centigrade, so and if it is at 110 degree centigrade, right. So, the difference is again it will be always at 4.1 millivolt. So, first case is 100 degree, second case is this is at 110 degree centigrade, but the output voltage still shows the reference temperature is 0 degree 10 degree. So, still the output from the thermocouple always shows 4.1 millivolt, because the difference is again 100 degree. So, it is very hard to understand by looking into the simply by looking into the output voltage 4.1, we will assume that the unknown temperature is at 100 degree, but actually speaking the unknown temperature is at 110 degree, the planned temperature is at 110 degree. That is because of we do not have any tracking system at our reference temperature. Suppose if I use LM35, right. So, by looking into the output voltage, so for 10 degree it shows 100 milli, right. We can understand yes it is at 10 degree. So, I say so 10 degree, this is nothing but 100 degree, this is 100 degree. So, as a result we can understand 10 plus 100, 100 plus 10, so which is 110 degree. But these are manual way of understanding, but if I want to correct it using an electronic system, right? I should always go with some temperature sensor which gives an output voltage, right? So if I say this is 10 millivolt per degree centigrade, which gives 100 millivolt for 10 degree, but I cannot directly add this 100 milli to 4.1 millivolt. The reason is that the sensitivity factor of this and sensitivity factor of this is different. So as a result, if I add it, it goes to some other value. So one way to do that is either we have to change the temperature sensor sensitivity factor to 41 microvolt per degree centigrade, or or the thermocouple sensitivity factor from 41 microvolt per degree centigrade to 10 millivolt per degree centigrade. Either this should be attenuated from 10 millivolts to 41 microvolt per degree, or the thermocouple output should be amplified from 41 microvolt to 10 millivolt degree centigrade. So which one is easy? By amplifying 41 microvolt to 10 millivolt is good one. The reason is that attenuating and the 2 microvolts from milli to microvolts, the signal to noise ratio percentage will be really poor, but whereas amplifying, the signal to noise ratio will be higher. As a result, rather than attenuating it, if I amplify the output of thermocouple to 10 millivolt per degree centigrade, it would be easy. So if I want to amplify from 41 microvolts to 10 millivolt, we have to use a sensitivity factor or amplification factor. So what amplification factor do I have to go with this? In order to understand what gain of an amplifier that I have to use, right, the output should be 10 milli, but the input is 41 micro. So that means if I take a calci, so 10 divided by 41, which is 0.243 into 10 power minus plus 3, because milli 10 power minus 3, 10 power minus 6, when it takes when I take it to upside, it will become 10 power minus 3 plus 6, 10 power plus 3. So that means 243 kilo, 243. So a gain of 243 has to be applied to the output of a thermocouple to get a sensitivity factor of 10 millivolt per degree centigrade, right? So how do we achieve this 243 gain, right? Either we can go with an inverting or non-inverting or instrumentation amplifier, right? So either we can go with a non-inverting and instrumentation amplifier other than going with an inverting amplifier. The reason is that the inverting amplifier may have some loading effect, because the output will be directly connected to the input of a resistor. The input impedance of this complete inverting amplifier depends upon the R1 resistor. If we choose a smaller resistance value and the voltages, output voltage of this one is really smaller, as a result there are chances of having a loading into the system. So as a result, rather than going with inverting, we can go with a non-inverting or an instrumentation amplifier. Now let me take up a small problem to make us understand about how to design a signal conditioning circuit. So the problem states that a K-type thermocouple is to be used in a measurement system to obtain an output of 2 volts per 2 degree. That means that if the plant temperature is 200 degree, the final system output voltage should be at 2 volts. So the gain, when you see the sensitivity factor, it is nothing but 1 volt per 100 degree centigrade, or I can say 10 millivolt per degree. Right, that should be the final system sensitivity, right. So that by looking into the output also we can understand what is the temperature acting on the plant, on the sensor. So we should design a signal conditioning circuit for the thermocouple such that to compensate for the temperature variation, the cold junction or reference, meaning even if your cold junction or reference temperature is varying, it should not have any effect on your output voltage. So that means if your unknown temperature, if the plant temperature is at 100 degree centigrade, but the room temperature is keep on varying, it should always show 1 volt, no matter what your room temperature is at, it should always show output as 1 volt, right. So in order to do that, what they are saying is you can either go with an solid state temperature sensor at the reference for temperature correction. So So, the solid state temperature sensor, whatever they are choosing at the reference, is a 3 terminal input. So, because we are using LM35, which is a 3 terminal, and the sensitivity factor is 10 millivolt per degree centigrade, whereas a K type thermocouple with a reference of 0 degree centigrade will give an output of 8.2 millivolt per 200 degree centigrade. So, when we calculate the sensitivity factor, it comes as 41 microvolt per degree centigrade. So, one thing is clear, but finally we should get output as 2 volt per 200 degree centigrade. How do we do that? So, as we have discussed here, if I use a gain of 243 to an what is this, a thermocouple, we can get an output as 10 millivolt per degree centigrade, but still the correction factor has not yet done. In order to in order to not to have any influence of your reference temperature, the output of this LM35 or the temperature sensor has to be added with the output of thermocouple, the conditioned thermocoupled output, right. So, what we are doing is, so we have calculated the gain as 243.9, which is 244, right. Now, what about the final output circuit? We require the finally 2 volts has to be shown for 200 degree centigrade. So, that means 1 volt for 100 degree centigrade. Right now, if I multiply with a gain of 244 and even still consider that we are compensating for the circuit, I will discuss how do we compensate it. If you see that, we will get a gain, will get an output as 1 volt per 100 degree. So, that means the final output, the final gain should be 2 by 2, which is nothing but 1. We do not need any gain apart from this, but how do we compensate? So, for that what we are doing is, we have to add the output of the thermocouple to the output of LM35. As a result, any change in the reference temperature will be automatically added. If it is at 0, the output will be added with 0. So, as a result, it gives the unknown temperature. If this is varying, obviously since both sensitivity factors of LM35 as well as thermocouple are same, so it will be the output voltage will be added according to the reference temperature value. As a result, it will show you the correct value too. So, the final circuit looks like this. So, how to understand this? So, this is basically a pot. So, when you observe that this is a non-inverting amplifier, this is our solid state temperature sensor, which is 10 millivolt per degree centigrade. So, consider thermocouple Tm is at 200 degree centigrade, right. So, if it is 200 degree centigrade, what is the problem says that if it is 200, if you apply the sensitivity factor of 41 microvolt per degree centigrade, it gives an output of 8.2, right. See, so this will be 8.2. In this case, the reference temperature is at 0 degree centigrade, consider it, right. So, we are using a gain, we should use a gain as 243.9, right. So, since it is a non-inverting amplifier configuration, right, non-inverting amplifier configuration, sorry 8.2 millivolt, this is 8.2 millivolt. I require to have both sensitivities to be of same. So, which should be 10 millivolt per degree centigrade, right. So, if I multiply the gain of 244 for 200 degree centigrade, I will get an output as 2 volt for 200 degree. So, observe what is the gain of the system, 1 plus R2 by R1. So, 1 plus 570 by R1 should be 244. That means 570 by 243, 570K by 243 should be the R1 resistor. So, when we calculate the resistance value, right, 570 divided by 243, we got it as 2.34 kilo ohms, right, we got 2.43. So, if I use a 2.34 kilo ohms resistance value, I will get an output voltage as 8.2 into 244, right. So, when I calculate that 8.2 milli into 244, I will get it as 200 milli, which is nothing but 2 volt, right. But what if this reference temperature is not at 0? For example, like say the reference temperature is at 50 degree, right. If this is at 50 degree, do we get an output as 8.2 milli? No, even though the unknown temperature or the measuring temperature is at 200 degree, but the difference in the temperature is 150 degree, the output voltage will be 150 into 41 microvolt per degree, right. So, alone this circuit, alone this particular circuit, it cannot compensate. So, if I do the calculation, 150 into 41, right. So, it will be 6.1 millivolt, right. So, for reference temperature of 50, we will get an output as 6.1 millivolt. Now, if I calculate the output voltage, it will not be at 2 volts. So, 6.1 into 244, I will get it as 6.156 into 244. So, it is nothing but 1.5 volt, the new value is 1.5. So, when we understand what is the unknown temperature, by looking into the output voltage we will understand it. So, when I look into the 1.5 volts, what do we understand? If I say the sensitivity factor is 10 millivolt per degree centigrade, we will understand that the voltage is at 150 degree centigrade, unknown temperature voltage is 150, but actually speaking the unknown temperature voltage is 200. That means with a simple first op amp we cannot compensate. How do we compensate? So, I will be choosing another temperature sensor LM35, where the sensitivity factor is also 10 millivolt per degree centigrade. So, when I place this on the reference junction on the same plate, on the same reference junction, so this gives me how much? 50. Since it is 50, 500 millivolt. That means it gives an output as 0.5 volt. So, this is an isolation amplifier, this also gives an output as 0.5 volts, right. So, now what is this? This is an adder circuit, isn't it? 10k 10k, so the gain is 1. So, 1.5 plus 0.5, I will get an output as minus 2. Because of inverting configuration, we will get an output as minus 2. So, when you see the complete system output, it shows you 2 volts. Forget about the phase, look into the magnitude of this, we will get a 2 volts. When you look into the 2 volts, we can understand that 2 volts is nothing but 200. So, that means here unknown temperature is at 200 degrees centigrade. So, this way by simply adding unknown temperature value, right, to your output voltage, where both the system should have the same sensitivity factor, we will get an value. So, how do we change the phase? If I want to change the phase, we can use one more inverting amplifier configuration here with a gain of 1k or 10k 10k. So, 1k parallel to 1k, this is nothing but 500 ohms. This is to eliminate the effect due to the bias currents, right. We get 2 volts as an output. Now, what if? So, one condition we have seen. What if the unknown temperature, this is at 200, consider this as 200, finally I should get an output as 2 volts, but the reference temperature is at 25, consider 25 degree. Now, will this value will be 8.2 milli now or 6.1? No, right. Since the reference temperature is changed, right, we will get an output as so when we say this is a compensating, that means it should always show at 2 volts when your TM measuring temperature is 200 degree, no matter what your reference temperature is at. So, since it is 25 degree centigrade and we know the sensitivity factor as 41 microvolt per degree centigrade for thermocouple. So, now the difference is 200 minus 25, which is 175 degree, right. 175 degree. So 1 degree corresponds to 41 microvolt. So 175 degree will be how much? So 175 into 41 micro, the value will be, when I calculate 175 into 41 micro, this is nothing but 7.175, yes, 7.175 millivolt, right. So now the new value is 7.175. Now what is the gain of first op amp? 244. When I multiply 7.175 milli with the 244 to get an output voltage of op amp 1, right, observe, into 244, that is nothing but 1.75 volts. So now the new value is 1.75, right. So only if I look only the output of op amp 1, we can understand it is at 175, but actually speaking it is not at 175, it is at 200 degrees centigrade. But when I look at the output voltage at this point, so since this temperature sensor is also at this reference junction, since it is at 25 degree, LM35 gives you an output as 0.25 volts, isn't it, because sensitivity factor is 10 millivolt per degree centigrade. So 10 milli into 25, which is nothing but 2.5 volts, sorry, 0.25 volts, right. So this is nothing but 0.25, right. So what is the gain of this op amp 3? The gain of the op amp 3 is simply 1, and this is an adder circuit. So we will get an output as minus of 1 into 1.75 plus 0.25, we will get output as minus 2. So we have one more op amp configuration here which changes the phase to 2 volts. So as a result, no matter what, so it is showing 2 volts for 200 degrees centigrade, even though the reference junction temperature is keep on changing. So by using this particular circuit, we can simply compensate for the effect due to, we can correct for the effect due to the temperature at reference junction. Now since we are using non-inverting amplifier configuration, we are using so many number of op amps and resistors. What if I go with an instrumentation amplifier? If you understand the instrumentation, 3 op amp based instrumentation amplifier, the advantage is it will always have higher CMRR value dB, since the reference since your output of thermocouple is also microvolts, which is almost close to 0, we should always have to go with an higher CMRR in this case. So which will be useful if you go with an instrumentation amplifier too. And another thing is that we need to also have an adder circuit, right, and input impedance should be always higher. Now if you see instrumentation amplifier will always have very high CMRR value, sorry, input impedance too, input impedance, right. And we also have to apply a gain of 244 to our thermocouple, right. So in this case, by using this op amp 1, we are setting a gain of 244, and even with an instrumentation amplifier we can design, we can choose a resistor value such that it gives a gain of 244, right. But what about adding of this the output of LM35? So rather than using these 3, right, if you refer your any instrumentational amplifier op amp, right, 1 and 8 will be always gain. So we can choose a resistor such that which has a gain of 244, and 2 and 3 is nothing but minus and positive, right. 4 is minus VCC, right, 5, 6, 7. So now let me open instrumentation amplifier. So I will take INA 128, in this case I will be using INA 128 instrumentation amplifier. So this is both for INA 128 and 129. If you see at this point, right, 1 and 8 RG, So, Rg, by choosing Rg as a proper value, we can get a gain of 244 in this case, sorry, this one 244. So, if I connect the thermocouple to V in minus and V in plus, rather than connecting a reference to simply reference to ground, if I connect the reference value from the temperature sensor, LM35 temperature sensor, whatever the output voltage will be the addition of V naught plus this reference value, which gives an output as V naught, the correct temperature corrector factor. So, as a result, with a single instrumentation amplifier IC, we can even design the circuit, right. So, this is our 2, 3, 4, 5, 6 and 7. So, this is our V reference, this is our V naught, this is our VCC, right. Rather than connecting V reference to ground, what I will do is that I will connect it to temperature sensor output. Now, since the gain of this is also the gain of this op amp instrumentation amplifier is 244, the output voltage will be 10 millivolt per degree centigrade, and temperature sensor gain is also 10 millivolt per degree centigrade. If any reference junction temperature is changing, as a result the reference voltage will be changing. So, that means the V naught, now the V naught will be addition of whatever the voltage we get plus V reference value. So, which will be equal to this way. So, with a simple instrumentation amplifier, even we can construct cold junction compensation circuit. So, let me show you thermocouple. So, if you see, this is it has an internally two dissimilar wires. Now, this is one junction where the measuring unit will be. This is where the unknown temperature can be the unknown temperature unit can be connected to, and whereas this is the reference junction. Okay. So, since these are of two different metals, you can see two outputs here, one from one single metal, other one from another metal, right. So, these two should be always onto the same junction, right. So, that since this two has to be placed on in the reference junction, since this two has to be placed on the reference junction, right. So, whenever any temperature sensor, another temperature sensor is connected, it should be connected close to this one, right. So, this is what we have seen in our module. So, in this case I am not going to show any experiment. The reason is that it requires the heating unit, and we should understand what is a known temperature in order to compensate for that. So, rather than that, I just explained you using a multisim to make you understand about how do we compensate, how to design a signal conditioning unit in order to compensate for any effect due to a change in the cold junction temperature. Let me show you the working of this using a multisim. So, since thermocouple is a self generating, I will consider as a voltage source, considering as a voltage source, but the value should be in a microvolt. So, what I will do is that let me set it as 8.2 millivolt, because 8.2 millivolt is an output from thermocouple if the TM temperature value, one junction temperature is at 200 degree, another junction temperature is at 0 degree, right. Just for us to understand, I am taking a non-inverting amplifier configuration. The positive is connecting to the output of thermocouple, another terminal should be ground, whereas we need two resistance. This should be 2.34, or you can take a pot 2.34 kilo ohms, and one more resistor here. The value of this resistor should be 570 K, 2.34 and 570 K, 570 K. Now, if I measure the output voltage simply at this point, let me run this. I have to close this, delete this, delete. If I run the circuit, we can see if the thermocouple is at 200 degree centigrade, we will get an output as 2 volts. But what if the reference junction is not at 0 degree? So, one case we have seen, if it is a 6.1 milli, if your reference junction temperature is at 50 degree centigrade. So, we got 1.5 volts, right. So, simply with one particular op amp, we cannot compensate for the temperature correction at cold junction. So, for that we are using one more temperature sensor. So, I am representing temperature sensor, the output with V2 voltage, right. So, if it is at 50 degree centigrade, so as per the temperature sensor sensitivity 10 millivolt per degree centigrade, we will get an output as 0.5. So, this V2 is a realization of your temperature sensor, and I am taking voltage follower, simple voltage follower. So, positive I am connecting temperature sensor output, I am connecting it to here, and the output I am connecting it here, right. Now, I will take another op amp which acts as a difference amplifier. This should be tilted and rotate. So, we have chosen this as 10K, I am also taking it as 10K, one more 10K at the feedback, and this should be connected to ground. Actually speaking, this should be connected with the 10 kilo, 5 kilo ohms resistor in order to remove the effect due to the bias currents. One more 10K at this point, it acts as an adder, connecting it here. Now, observe the output voltage at this point. Now, 6.1 millivolts at V1 corresponds to the output from thermocouple, which means that if your reference junction temperature is at 50 degree centigrade, and whereas thermocouple another junction temperature is at 200 degree centigrade, the output voltage that we get will be 6.1. Now, because of the reference junction temperature sensor, reference junction is at 50 degree, since we are placing another temperature sensor which is V2, so it shows an output as 0.5. Now, when I run the circuit, still we can see minus 1.99, which is nothing but minus 2 volts. No matter what, since we are using compensation by placing another temperature sensor on signal conditioning circuit, even if your reference junction temperature is at 50 degree, we will get an output as minus 2. Suppose if it is at 25 degree, we know that the value will be 7.175. So, I am changing it to 7.175 millivolt, right. When we see that, so that means this voltage should be 0.25, right. Still we can see that minus 2 volt. So, no matter what, if you change the reference junction temperature, right, if you change the reference junction temperature, it will always be at minus 2 volt. So, it is compensating.